Hello class, let's continue with where we left off talking about transistor amplifiers, and this time we're talking about power amplifiers. We did look at a small amplifier, two transistor amplifiers used in this particular small Bluetooth wireless amplifier speaker, and we did see how these transistor amplifiers can be used to drive your output, especially a speaker in this case. But let's look at how they can be configured in different applications, for audio applications as well as for high frequency applications, and how do they are classified based on how, at what frequency and what cycle of conduction do they have. Let's look at it in detail. So in this session, we're going to be looking at transistor amplifiers in terms of the classification, class A, B, C, AB, and as I mentioned earlier in the practical session I just mentioned about in passing, I talked about this class D amplifier, which is not part of your syllabus, but we will see this also in passing, so that you know what is available in the market, at what price and what size and what efficiency. It's considered to be really high efficiency. It does not require a heat sink because it does not get that hot at all. And why? So we'll be looking at class A, B, C, and AB and their comparison in terms of the operating point, the conductivity, the conduction cycle, their efficiency, and the applications. As per your examination, there's no circuits required and you're not expected to remember them. We did see these amplifiers, the large transistor amplifiers used, and I mentioned that I will show them in detail. For example, if you look at an amplifier, at the back you would see these four studs. These are actually these transistor amplifiers protected with a small plastic cover so that they're not damaged in transit. So those are exactly what we're talking about. Those are the transistor amplifiers we're talking about in terms of using an audio application to drive large speakers in auditoriums and for your outdoor events where you have large speakers to be driven. These are the types of transistor amplifiers that they use. So talking about the classes, what are the difference? The simple class A amplifier is not very efficient. It has about 30% efficiency, but the beauty about it, it conducts 360-degree of your input. So in other words, if I give 0 to 360-degree variation on my input, the same variation is seen on the output. The gain is not that great and the losses are really high. The amplifier heats up a lot, but it's rarely used. But that is a beauty about the transistor amplifier in class A, is it can conduct the entire 360-degree to the next stage. On the other hand, we have class B amplifiers, as you see here, which can only conduct 180-degree of your input. In other words, the other phase, other 180-degree is not conducted. So you would need two class B amplifiers, one to conduct the positive cycle and one to conduct the negative cycle, to be able to drive it together. So they call it a push-pull configuration. But the problem with this, every time it's crossing zero, there's a switch over from one transistor to the second transistor, and there's a problem with that switchover. To avoid that problem, we have a combination class called class AB amplifier, which does not exactly conduct all the 360, but it does not have the problem of the zero switching problem. So you have a diode integrated inserted into the circuit where it does a conduction between 180 and 360. So it does have the problem avoided with class B, but it's not the perfect amplifier. You also have class C amplifiers, which don't conduct all of that is expected, but they're suitable for very high frequencies. So you'll be able to amplify, you'll be able to get an output, but the exact waveform of the input does not match the output because a lot of it is clipped out. You have a small amplitude of the input that's matched, and that's what is amplified. So you do have applications for class C in high frequency applications. For example, we talked about this simple audio amplifier. So we had two transistors where the gain is amplified. We saw that earlier. Now, we talked about the bandwidth of operation and the frequency response. Let's look at it. So classifying amplifiers based on frequency efficiencies, you have class A on the lowest, where it does conduct 360-degree. Then you have class AB, the combination, it's better than B, but it does not conduct all the 360. It's between 180 and 360, and it has there's no problem with the zero. But you have class B, it conducts 180 perfectly. It's good, but about 50 to 60% efficiency. You have class C, suitable for high frequencies, but does not conduct the entire cycle. Then you also I mentioned about class D, which works on pulse width and is presumably considered to be about 100% efficient in theory. Let's look at it in detail. As we saw the diagram earlier, so not all amplifiers are perfect. Not all amplifiers serve the purpose, but we identify the one that ideally meets our requirement. So what do we look for? Does it amplify linearly? In other words, when you're talking about what frequency does it amplify and what does it linearly amplify? In other words, does it have a particular point where it distorts? We look at signal gain. Gain is, in other words, how much do we have a gain compared to the input to the output? What difference does it have and how much does it have uniformly for an entire frequency band? Efficiency. I give an input, I'm expecting an output. And how efficient is it? Talking about the power output level. So you're talking about power amplifiers in this case. So we're talking about real world applications of amplifiers. We also talked about audio amplifiers and we talked about impedance matching. So if you remember the fundamentals of electronics, or you talk about maximum power transfer theorem, when the internal impedance of a circuit matches the external impedance of the circuit, maximum power is transferred. That's why we have impedance matched for our external speakers. Which says it's a 4-ohm speaker, connect to 4-ohm, impedance is matched, it works efficiently and it works with maximum power conditions. If your impedance of transformers or your application is not matched, you'll be overloading your speaker or you'll be overloading your amplifier, and that would not be a perfect consideration, a perfect example or application. Then we talked about class amplifiers. Yes, let's look at it. So it's a very simple amplifier. If you look at the circuit, you can see it. It does have the beauty of conducting the entire cycle, where the center point is right in the middle, so it can conduct positive cycles and negative cycles, and it's more or less, if it's considered to be linear, it does a good job. But the problem is the efficiency is not that great. It's about 30%, and you would have a lot of heat being dissipated since the efficiency is very low. Class B, as we know that it can only conduct 180 degrees, so you have two transistors, one NPN and one PNP combined together. One does the positive cycle, one does the negative cycle, you get 180 degrees of the output. But the problem is when you're switching from one transistor to another transistor, you have distortions, which is undesirable. And that's why we talked about the next version of transistors, which is class AB. We overcome the problem by inserting a small diode which takes care of the problem of switchover, but it does not conduct the entire band. It's predominantly between 180 and 360 of conduction. The efficiency is much better, about 50 to 60% compared to class A. And class C amplifiers, it does not conduct the entire band. It's suitable for really high frequencies, and it's comparatively better than your class A, B, and AB, but it has a lot of distortion because it cuts out most part of your output. There's a small part of your output which is available, and your parallel resonance circuit is here, which causes it to stay within the high frequency range, but is not the perfect. But looking at what the power is being transferred, the efficiency is about 80%. So talking about the efficiency is all about output by input. It doesn't matter is it conducting the entire band? No. Talking about how much output do I get, but how much input have I given in terms of amplification. It does really have high amplification. But there are other classifications, as I talked about the class D amplifiers. Theoretically, it's about 100%. In other words, it does not have high losses, it does not generate a lot of heat, and it does not need a heat sink. And the other ones that are used in really small boards like your Bluetooth speakers, your portable small amplifiers, you use class D amplifiers. So as I talked about pulse width modulated amplifiers, yes, those are the ones that have nonlinear switching, but it does cover the entire spectrum and it's pretty efficient. And that's why we're able to get amplifiers as small as the one I had showed earlier in the picture. So this is a class D amplifier. It's pretty small and it can even drive a big speaker and give you a decent amount of output. And you can see a lot of tutorials on them on the internet. You can make your own. I've made one and I've desoldered them at the moment, so we can put them back together to drive some speakers to show you exactly how they work. So talking about amplifiers, we saw that in detail over the entire spectrum. Class A, it conducts the 360 degree, but it's not very efficient, so you have about 30% efficiency. We talked about class B to be doing about 180 perfectly. Efficiency is not that great, but since you can combine two of those transistors together and be able to get a 360 degree transition from input to output, decent output, amplitudes being amplified. But there is a problem when it switches over from 0. You would have problems where the there's a dead band on the 0 part. To avoid it, you have class AB amplifiers developed, which is a combination of class A and B. And we notice that it does not completely conduct the entire band because you're taking care of the 0 part by having the 0 pushed over across the linear band of amplification, but it conducts between 180 and 360. It does this possible. It's possible because you have a small biasing voltage required to get over a diode before the input goes to the output stage. Then you talked about class C amplifiers. They are very efficient, but they don't conduct entirely. They are talking about anywhere between talking about between the ranges of 180 and 360 on in between bands. That's where it can amplify, and it does good. It has really high efficiencies, about 80%, but there is distortion. And we also talked about, in modern applications, you talked about class D amplifiers, which is outside the syllabus, but we talked about it where it does a really good job. It does not have much losses, theoretically about 100%, and the amplifiers work with pulse width modulation, and that's what is part of your syllabus in terms of amplifiers. So you talk about amplifiers as you talked about the pictures of transistor amplifiers. Yes, this you would look at it in detail in other cases where your transition between your input stage to the output stage would be driven through transformers. So if you look at a transistor based amplifier, you would also see heavy transformers used to couple the input stage to the output stage, and that's where impedance matching on the transistor stage plus impedance matching on your transformer stage is required to be able to get a desired output. Let's look at it this way. Let's look at a couple of amplifiers to see what makes them really heavy. So let's look at this picture. This is a picture of a typical Indian Ahuja amplifier, and you would see that the transformers that are required to drive it, one is your power transformer to drive your speakers, the other one is your power supply transformer, which is rectifying your AC to DC. These transformers is what makes amplifiers heavy. If you notice lifting an amplifier, you would notice it's really heavy because of these coupling transformers that are used, which are center tap transformers. You have two transistors driving your output stage, and they are driven through these transformers. So these transformers is what makes them heavy. You also have a look at another transformer that's used in other amplifiers, which is these toroidal core transformers. They are made specifically for the audio industry, and you would see this transistor at the back bolted to the heatsink so that they can cool down, and the toroidal transformer is there to drive your speakers, transformer coupled. And this transformer is what makes transformer based these kind of amplifiers, push-pull amplifiers, really heavy. So we've seen the classifications, we've seen them in practice to see how they are connected. Though a transistor can only conduct 180 degree, how do you combine two together to work in a push-pull sequence to be able to get the complete 360 degree amplification that's required for getting an audio range completely amplified to a speaker, as in this case of this Indian or these American-made transistor-based amplifiers. So that's it for the session. We will continue more in the upcoming sessions as we continue on with the syllabus in looking at oscillators in conjunction with transistors. That's it for now. If you have any questions, please drop in a message in the group, classroom group. Also, feel free to reach out through WhatsApp or email. Thank you and have a great day.